All right. So today in GRE prep land, we are going to be talking a little bit about some basic definitions in math. So we're going to be looking at the quant section, which is the more important section for most of you, considering that you're probably going into a health-related field, which is science-dominated. So they're going to be looking at your quant score more critically than your verbal score. So remembering that the quant sections, you get a little bit more time per question than you do in the others. It's also important to note that you do get a calculator, but it's not very functional. The only thing that the calculator does on the GRE is plus, minus, times, divide, and that's it. You don't have other functions like square root or squared or log or any of those other things. So if you're faced with some of those kinds of questions, you have to learn how to deal with them without the calculator. Basically, think of the calculator on this section as being really focused on just doing arithmetic. So if you've got some larger numbers you need to multiply or divide, that's when you start invoking it. Addition and subtraction you probably do by hand more easily than just opening up the calculator and using it. So a reminder here as well is that on the quant section, you're going to have 35% of the questions are quant comps, and we're going to have a session that we focus in on specific question types. 10% of the questions are going to be numeric entry, and 65% of the questions are just straight up multiple choice. But the bulk of them, the multiple choice, is going to be word problems, often on number theory and things like that. So let's start out with our vocabulary. What is our math vocabulary? Do we have the right vocabulary here? So the question at hand is, what's the difference between whole numbers and integers? What is the difference between a whole number and an integer? They use these terms on the test, so you want to know what they mean. What is the difference between whole numbers and integers? Somebody out there certainly knows this. What do you guys think? Anybody going to venture a guess? Seems like we don't want to answer today. There we go. That's right. Integers are negative and positives, while whole numbers are just anything from 0 on up. So why is this important? Because if they say in a question, what integer, da 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 da, or they say in a question, what whole number, da 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 da, you have to know the difference, because you don't want to be testing out negative numbers if the question is about whole numbers. And so, yes, this is math from what grade? This is math from 6th grade or before. And this is why it sometimes makes the GRE harder, because it's stuff that you don't remember. Positive versus negative, not going to stress about this one too much, because you know that positive numbers are positive and negative numbers are negative. What number is neither positive nor negative? That's right. 0 is neither positive nor negative. So if they're saying it's a negative integer, that does not include 0. If they say it's a positive integer, that does not include 0. So you would not want to include that in your thinking. That's right. What's the difference between even and odd? All even numbers can be divided by 2. That is right. So is 0 an even number? Or is it an odd number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an even number? Or is it an odd number? Or is it an Oh, it is one of the two. 0 is an even number, and this is weird, right? But 0 divided by 2 is 0. So it is divisible by 2 in the sense that it gives you a result that is not a fraction. So 0 divided by 2 is proof that 0 is an even number. So you should treat 0 as even if they're actually including that in your logic of the question. What's the difference between an improper fraction and a mixed number? What is an improper fraction? What's the numerator of an improper fraction? Yeah, the numerator is bigger in an improper fraction, and a mixed number is when you have a number with a fraction itself. That's right. So you might be looking at 4/3 versus 1 1/3. So if they're asking you for your answer in certain terms, they might actually phrase it differently. And then finally, what is the difference between rational versus irrational? Think of some rational numbers versus irrational numbers. Pi is an irrational number. And why is that? Because if you look at pi, does its decimal ever terminate? Or does it go on forever? Yeah, it never stops. So irrational numbers, they have an unterminating decimal. So things like 1/2, that is 0.5. So its decimal stops. Or something like 0.0 or 0.376 with the 76 repeating again and again, that actually is rational because any kind of repeating number can be turned into a fraction. And 1 is rational, of course, but things like pi, e, that's Euler's number, like the base of natural log, and then √2 or √3, those are irrational numbers. So again, why am I bringing this mathematical vocabulary up is because they might ask you for this in like the way they ask a question. It might be brought up that says, okay, what rational number, blah, 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 or which irrational number solves this equation, or things like that. And so you've got to know what the difference of those things are. You also need to know your divisibility rules. So what is the rule for divisibility by 2? If I'm going to look at a number and to say this is divisible by 2, what could I look for? Yeah, it's an even number. That last digit in the number is going to be even. How about if I'm looking for something that's divisible by 3? Is there a rule I could use to determine if it's divisible by 3? Like, so is 786,000 divisible by 3, and how would I know? In this case, it's not about the last digit, but the sum of the digits has to add up to something. What is the sum of 786,000? 7 plus 8 plus 6 plus 0 plus 0 plus 0. It's 21. So the sum of the digits is divisible by 3. Yes. So if I just add up all the digits of the number and I get 21 in this case, that's divisible by 3. That means the larger number is divisible by 3. How do I know if something's divisible by 4? Turns out the last 2 digits are important in this case. Is 24 divisible by 4? So that means the whole number is divisible by 4. So if you, because anything beyond that, we know if I'm in the hundreds, 100 is always divisible by 4, which means everything beyond that is going to be divisible by 4. But it's the last 2 digits that make the difference here. So if the last 2 digits are divisible by 4, then I know for sure that this whole number is divisible by 4. How about 5? What must my number end in to make sure that it's divisible by 5? It's got to end with 0 or 5. That's right. Divisible by 6? This is kind of a combo rule. We got to test it with both with which other 2 rules? So it has to be all the sum of the digits have to be divisible by 3, and it also has to be divisible by 2. Yeah, so basically divisible by 6 is just basically checking rules for 2 and 3. If both of those rules apply, then my number is going to be divisible by 6. Notice that there is no rule for divisible by 7, because 7's a weird, freaky number. It doesn't have easy, simple divisibility rules for it. Divisible by 8, the last 3 digits would be divisible by 8. So if I look at 240, I can divide that one by 8. I can't really just apply the rule for 4 and 2 in this case, because 8 it's a little more complicated than that. But I have to recognize that at least 240 is divisible by 8. That will actually work. How about divisible by 9? What did the digits have to add up to? It's very similar to the rule for 3. What do the digits have to add up to in the divisible by 9 case? Well, what do 2, 5, 6, 0, 2, and 3 add up to? They add up to 18, which is, in fact, divisible by 9. Yeah, that's right. So as long as my digits all add up to something divisible by 9, I can actually say that this number is divisible by 9. And then finally, if it's divisible by 10, what do I have to be? The number ends in 0. So again, these seem like kind of arbitrary rules, but this is some of the basic stuff that you don't remember from middle school that sometimes can affect you in figuring out your value or figure out your answers. So make sure you know your basic math rules like this. How about prime numbers? Numbers that are divisible by only themselves and the number 1. What is the first prime number? 7 is actually the 4th prime number. 3 is the 2nd prime number. 2 is the 1st. 1 is not prime. 0 is not prime. So because 1 is a weird case. 1 is divisible by itself, which is the number 1. So it's not divisible by itself and the number 1, which is the way math rules work. So 1 is not prime. 2 is prime, then 3, 5, 7, 11, 13, 17, 23. They love the prime numbers. They might give you a question that's all about, prime factorization, or what is the prime what is the only prime number that's, you know, a factor of this thing or something like that. So you do need to be able to recognize your primes when you see them. Prime factorization is a tool that actually is very useful for solving a lot of questions, it turns out. So what do I mean by prime factorization? It basically, you're going to find all the prime numbers that a number is composed of. So if I'm looking at, say, 45, let's prime factorize this thing. What's the lowest prime number that is a multiple, or sorry, that is a factor of 45? What's the lowest prime number that is a factor of 45? 3. So I can take a 3 out of this and I'm left with 3 times 15. Let's continue to factor this. So what's the next lowest prime number that fits into 15? Also 3. So I can break that down to 3 and 3 and 5. So now we have a prime factorization, which we can rewrite as 3 squared times 5. So prime factorization as a skill is very useful for many, many, many questions, not the least of which is when you're dealing with multiplying fractions. Because you can make your fractions a whole lot easier to work with if you weren't looking at this mess. Like 12 over 5 times 14 over 3 times 9 over 21 times 5 over 24, that looks like you're going to get some really giant freaking numbers. But no, let's factor each of the terms into their prime factors. So what can I factor 12/5 into? Like, what are the factors of 12? Two 2's and a 3. So 2 squared times 3. What are the factors of 14? 2 and 7. What are the factors of 9? It's going to be 3 squared. What are the factors of 21? 3 and 7. And what are the factors of 24? 3 2's and a 3. So 2 to the third power times 3. So if I rewrite my fractions like this, all of a sudden we have a very powerful tool here, don't we? Because now I can just simply cancel out many of these factors. Like I can say the 5 cancels with 5, the 7 cancels with 7. I've got 3 2's up top and I got 3 2's down at the bottom. I've got 3 3's up top and I've got 3 3's on the bottom. So what is the answer to this problem? If all of the factors cancel out, I'm going to get 1. I get 1 over 1 times 1 over 1 times 1 over 1 times 1 over 1, and you get, in the end, 1 is your final answer. So this is very illustrative of what the GRE tends to do. They give you really complex looking problems, but the answers, the solutions to those problems is usually very simple. There's not a lot of complexity to a lot of these answers. So that's something you want to keep in mind, is that even though the questions might look scary, if you just take a little time to break them down into their parts, they're generally not that bad. And this is where prime factoring can really shine, is helping you with questions like this. Or when you're dealing with dividing fractions as well. And does anybody remember how division of fractions works? So if I have 12/5 divided by 14/3, what do I have to do? Yeah, I'm just going to multiply by the reciprocal of it. So what this problem is saying is I'm going to have 12/5 times 3/14 times 21/9 times 5/24. So it's the same kind of problem. If I put my prime factors into it, then I can just start canceling stuff out. So what's going to cancel in this case? Looks like my 7 goes, my 5 goes. I've got 2 2s up top, so I can only cancel out 2 2s here. So I got to leave 1 down there. Then I've got 1, 2, 3 3s, so I can cancel all my 3s. So what's left behind this time? What's going to be my final answer in this case? Well, I have 2 2s left in the denominator, right? I've got this 2 and I got this 2. So I should end up with 1/4. Yep, because I have 1 times 1 times 1 times 1 over 2 squared, which is going to be 1/4. So there we go. And I know you have a calculator and you might be thinking to yourself, like, why can't I just use the calculator to do this? There's a lot of problems with doing fraction math with the calculator, which doesn't have the parentheses function, because it doesn't have parentheses. You can't do that. So you have to actually do a whole lot more work to do this kind of thing in the on-screen calculator. So it's good to be able to deal with fractions in this way. Another use of prime factorization is dealing with least common denominator or least common multiple, because least common denominator is an application of least common multiple. So if I'm going to add these two fractions up, I want to find the least common denominator between them. So how do most of you find least common denominator right now? If I had to add these two fractions, what do you think you would probably do? Guess and check. We don't that's actually common practice. We probably don't want to be doing that though, because it can take a lot of time. We want to be able to find the common denominator for these things very quickly, so we can add these things very quickly. And what I'm guessing a lot of other folks are doing is they're multiplying the two denominators. Yeah, there it is. Multiply the two denominators together. So 21 and 24 is your common denominator. The problem is your answer won't have that as a common denominator, because the common denominator of these is not 21 times 24. To really truly find the common denominator, you should factor these things. So what are the factors of 21 and 24? So what are the factors of 21? Let's start there. 3 and 7. And what are the factors of 24? 2 cubed times 3. So what you want to do for least common denominator is find all like common factors and only use the ones that are not in common. So I already have a 3. I don't need this 3. So I can cancel that 3 out, and really my common denominator needs to be a combination of 3, 7, and 3 2s. So I should have 168 as my common denominator. If you did 21 times 24, that's not the same value. You're going to get something much, much greater than that. So finding common denominator is finding the least common multiple of these things. So you don't want to just multiply the two fractions together because that gives you larger numbers, and larger numbers are generally harder to work with. So let's add these two fractions up. What are we going to have to do to get to the value we're looking for? So we know our common denominator is 168. So what do I need to multiply that first fraction by to get it to 168 in the denominator? I'm gonna have to multiply it by 8. So do I just multiply the numerator or the denominator, or both, by 8? Both. And what am I going to multiply the second fraction by? By 7. So I do that to both fractions, and I get 32 over 168 plus 35 over 168. So what's my final answer? $67 over 168. And can I simplify that at all? Nope, because 67 is what kind of a number? It is prime. 67 is a prime number. So another reason to know your primes is actually so you can know if you have to simplify fractions at the end of doing a problem, say. Alrighty. Now, being able to work with fractions and decimals and percents all sort of in realizing they're all equivalents is actually an important skill here too, because they love their fractions, they love their percent questions. You want to be able to just to treat them all very quickly. So what is the equivalent of 1/2 in decimal form? What is the equivalent of 1/2 in percent form? %50. How about thirds? What's 1/3 in decimal and percent form? .3 repeating and 33.3%. Yep. How about fourths? What's 1/4 in decimal and percent form? 0.25, 25%. How about a fifth? Now we're starting to get into some deep cuts in the fraction world. 0.2, 20%. Notice I skipped over 6, 7, and 8. They generally won't use fractions like that if they're doing percent problems. They're generally going to be doing something that's a quick and easy. How about ninths? This one seems like it's a deep cut. It is, and people tend to forget this. Yeah, 0.11 repeating and 11.1%, because if 1/3 is 0.333, 1/3 of 1/3 is going to be 0.111. This also is a nice party trick. What's 9/9 equal to then? A little bit of a math insider joke. 9/9 is equal to what? Nope. It's equal to 0.9 repeating. Did you ever think about that? If 1/9 is 0.1 repeating and 2/9 is 0.2 repeating and 3/9 is 0.3 repeating, then 9/9 has got to be 0.9 repeating. It's actually funny enough. This is actually a problem with modern mathematics. So, like, how does that actually work? Is 0.9 repeating actually 1 or what? So there's a lot of weird proofs out there to try to prove that 0.9 repeating is the same thing as 1. Go figure. So yeah, that's a thing. That's totally a thing. And then how about tenths? What's 1/10 in decimal and fraction or percent form? .1 and 10%. That is correct. So being able to flexibly use fractions is important. They love their percents, they love their fractions on this test, and you just want to be fluent in that. Percent difference, another favorite of the GRE. You've got to remember what percent difference means, which is the difference over the original. Notice how I have that in bold, the original value. It's not the difference over the new value, it's the difference over the original value. So here's an example question of something they might do. The price of a computer was discounted $15 from its original cost. Sven paid $85 for the computer. What was the discount as a percent? What is the way that many people accidentally, what's the trap answer here? What are the not 85%. I wouldn't call that the trap answer. But yeah, that's the trap answer. The trap answer is 15 out of 85 because those are the two numbers that are in the question. And so people will have a habit to go ahead and just say 15 over 85. That's not percent difference, however, because the percent difference is got to be difference over the original. So what's the actual answer for this question? Because this ain't it. It's 15% because it's got to be 15 over 100 because the original price was $100. It was 15 was the discount and the original was $100. So it gives us 15%. So now, like, why do they do this? Well, because they're certain that people are going to just pop 15 over 85 and that answer choice will be there. They will give you a 17.6 and it's very attractive. And it's probably like answer choice A or B because it's one of the first ones you're going to look at. And so watch out for that with, oh, well, actually this is numeric entry. So they wouldn't have actual answers like that. But if it was a multiple choice answer, then that would be a potential answer. So they know that that's a very easy thing to slip into because the numbers in the question are 15 and 85. So do be wary of that. The GRE is not hard. It's tricky, it's sneaky, it's mean. So yeah, that's the kind of stuff we're going to see on the GRE is this sort of trickiness that they try to put into a lot of the questions. Oops, there we go. So do we remember how things associate, distribute, and commute? So what does it mean, association of addition and subtraction? What do we mean by that? It means that 3 plus the quantity 2 plus 4 is the same thing as the quantity of 2 plus 3 plus 2 plus 4 is the same. So addition and subtraction associate. That it doesn't matter what order you do it, you get the same actual result. However, subtraction, that doesn't work. If you do 3 minus quantity 2 minus 4, that's different than 3 minus 2 quantity minus 4. So addition associates, subtraction does not. So you can do any order for addition, but you can't do any order for subtraction. You got to follow that order of operations. And it's very similar for multiplication and division. Multiplication associates, you can do it in any order, but division does not. If I do 3 divided by quantity 2 divided by 4, that's different than 3 divided by 2 divided by 4. So you just got to be careful in the order in which you do things. Basically, I think the lesson learned here is always use the order of operations, which I'll give you guys the preview of that in just a second. Of like, not the preview, but the mnemonic that I use for it all the time. Commutation says I could just change the order up. And again, it works for addition, but it doesn't work for subtraction. The same goes for multiplication and division. 3 times 2 is equal to 2 times 3, but 3 divided by 2 and 2 divided by 3 is not the same thing. So you have to work from left to right on these types of questions. And then distribution means things can multiply through. And this is a rule that so many people forget. If you have 3 times the quantity 4 plus 2 minus 5, you have to multiply the 3 times every single part of that quantity. So it's 3 times 4 plus 3 times 2 minus 3 times 5. Division does the same thing. If I have division of that quantity, I have to put the thirds on each of those. So it's 4 thirds plus 2 thirds minus 5 thirds if I'm going to do it in fraction form. So don't forget your rules of association, commutation, and distribution. The one I think most people struggle with is distribution. Now, I did mention order of operations. You always want to follow your order of operations. And does anybody remember PEMDAS? Is that a thing? Please excuse my dear Aunt Sally. Now, what happens is a lot of people remember this wrong. Parentheses, exponents, multiplication before division? No. Multiplication and division from left to right. So you do multiplication and division, they're equivalent to each other. So you work them left to right in order. And then addition, subtraction, addition's not more important than subtraction. So you want to do those both together from left to right. So if I have a problem that looks like this, what is the first thing I should probably do here? According to the order of operations. Start with what's inside the parentheses, and inside the parentheses, what should I do there first? I'll do the exponent. So I've got 16 in there for the 4 squared. And then what do I do next? Go ahead and do that division inside the parentheses. So I get 16 divided by 4, which is 4. Now what do I do? Since I've got to do multiplication and division from left to right, I'm going to start with 10 times 4, which is 40. Then what am I going to do? The 2 times 4, because I'm going to continue from left to right, that gives me 8. Then what? Eight divided by 2, which gives me 4. Then what? The 4 divided by 1/2, which is equivalent to 4 times 2, that's right. So it gives me 8. Now what do I do? $40 minus 8, because I'm going to do my addition and subtraction left to right. So that gives me 32 plus 10, which gives me my final answer of 42, which is, does anybody recognize that number? It's a little inside joke. They, surprisingly enough, they use these inside jokes on the GRE quite a bit, but 42 is a pretty common answer. The answer to the life, the universe, and everything. Little Douglas Adams reference. No? You guys got to read the Hitchhiker's Guide to the Galaxy series. All righty. Now, there is a mnemonic device for remembering how to deal with exponents as well, and that is MADSPAM, M-A-D-S-P-M. When you multiply two numbers that have exponents, you can add their exponents. If you divide two numbers with exponents, you subtract their exponents. If you do a exponent to an exponent, its power, you can do multiplication of those exponents. So this is an actual problem from an actual past GRE. So if I look at this thing, I'm going like, gee gads, how do I deal with this? Can you do this with the on-screen calculator? No, there's no exponent possible. And plus, this would probably make your on-screen calculator puke. But if you just follow the concept of exponent operations, this is a totally, like, surprisingly enough, this is a very simple question. It just doesn't look simple. So let's deal with some of these exponents. So I can apply the power rule to the denominator. So if I look at the denominator, what could I turn that into? 7 to the 12th to the 3rd. What would I do with the 12 and the 3? It's going to be 7 to the 36, because it's a power of a power, which means I just multiply those exponents. What could I do in the numerator with the 27 and the 10? I've got 7 to the 27th times 7 to the 10th. And notice I'm still following my order of operations. Exponents go first, and then multiplication goes next. So that's 7 to the 37th. Then what could I do in the numerator to simplify that numerator? Is there any way to simplify that? I can't actually simplify it. So what would I have to do? I'd have to distribute the 7 to the 36th. I could turn this into 7 to the 38 over 7 to the 36 minus 7 to 37 over 7 to 36. But now I can actually simplify this, because what is the first fraction simplifying into? Yeah, it's going to be 7 squared. And what is the second fraction simplify into? Just 7, because it's 7. When you're doing division, you subtract the exponent. So I'm going to get 7 squared minus 7 to the 1st. And again, I was able to get my little joke in there again. And the answer is 42. So all that mess turns out to be 42. And this is what the GRE does. It hides very simple answers in very complicated clothing. And so you just have to, like, not get stressed out by it, but realize it probably is, there's always, like, it's not even probably, there's always a way to simplify these problems that you're going to run into in the GRE. And it just might take worrying about things like roots or fractions or powers or, distribution, all this kind of fun stuff. Now, as far as roots go, square roots and all that fun stuff, you can't actually do square root or powers on the test. So you got to understand how to work with roots as exponents. So first off, roots are fractional exponents. So if I have something like square root of 5, how could I rewrite square root of 5? What is the power that I would put for 5? Yeah, so square roots are going to be that 1/2 power, or cube roots are going to be that 1/3 power. And the reason we want to turn roots into powers sometimes is because that way we can deal with it using the exponent rules that we just talked about. Another thing is when you're dealing with square roots, you got to remember they're just like treat a square root like a variable. So if I have 1x plus 3x equals 4x, nobody balks at that. But when I see root 5 plus 3 root 5, a lot of times I see people like struggle with this. You're just really doing 1 plus 3 times root 5. So that's just going to equal 4 root 5. So you can add up roots like they're variables essentially. You can also, when you do multiplication of roots, you just combine the roots inside. So root 5 times root 3 is equal to root 15. And then you want to also be able to pull out like perfect squares. So if I have square root of 200, square root of 200, what does that give me? Are there any perfect squares in the square root of 200? Yeah, I've got 10. So I could pull out the 100 and say the square root of 100 is 10, and the square root of 2, that's the other factor, is still going to be root 2. Or in my case, I did it a little bit different. I said root 2 times root 4 times root 25 is the same thing as root 2 times 5, which is 10 root 2. So you want to be able to extract perfect squares from your square roots to pull that outside of the root. So you can simplify it down to simpler roots like root 2. Something to remember for roots, by the way, what is the approximate decimal value of root 2? And the way I remember this is Valentine's Day. Valentine's Day. When is Valentine's Day? February what? 14th. So it's 1.4. February 14th, Valentine's Day. I don't know why, but people don't seem to remember St. Patrick's Day very well, but hopefully you don't forget it after this. What date in March is St. Patrick's Day? March 17th. And the square root of 3 is approximately 1.7. So this is a weird little mnemonic, but it's actually very useful if you have to deal with square root of 2 and square root of 3 in a problem. Because and sometimes they'll do this, you'll need to reduce it down to something you could do math with on the calculator. Then 1.4 for root 2, 1.7 for root 3. And there you go. So wow, that was a lot of like very esoteric rules, right? Like things you haven't seen for a very, very, very long time for math. Like these are the things that actually get you, down, get you down on the GRE. So make sure you're very well aware of your math rules there. So that's what we were here for today. Next time, what we're going to do is we're going to actually look at plugging in and organizing our work. One of the things, one major important technique that you can use on the GRE is plugging in. And did anybody here take a test prep course for ACT or SAT? Then you probably learned about plugging in for your ACT and your SAT. And plugging in is you want to recapture that technique because plugging in makes some of these questions so much easier, especially quantitative comparisons. So we're going to talk about what that strategy is and also how just basically to organize your work into a nice clean set of notes so that it's actually, you're not losing sight of your actual question in there. So that's what we're going to do next time. That's next week. And we still have that GRE, mock GRE coming up soon. You should be able to sign up for it. I want to say this coming Friday, the sign up sheet should become available for that. And otherwise, thank you guys for coming today. Hopefully you learned a little bit, or at least refreshed a little bit on some of these concepts that you need to know for the GRE. The recording, the slides, if you want the slides, just email me and I can send those to you. The recording, I'm still working on that darn YouTube page. I'm relying on some other people here, and I'm trying to get them to help me out. So I will get the recordings up as soon as I can. I'm hoping this weekend I'll get all the recordings up. Distribution for multiplication, what we're looking at is that if you've got some number times a quantity, like 4 plus 2 minus 5 like this, that the number in front multiplies to each of the terms inside. So I can just simply say this is 3 times 4 plus 3 times 2 plus 3 times, or minus in this case, minus 3 times 5. So what I usually, like, if I'm working with students that are doing this for the first time, I'll actually have them write this, like, or draw this, that the 3 actually goes with each of those numbers. In the case of division, again, the 3 goes with each of those numbers. 4 divided by 3, 4 divided by 2, or sorry, 2 divided by 3, and 5 divided by 3. So I don't change the operations that are happening in the numerator or in the quantity, but I just add the 3 into each part of that individually.